Dear students, welcome back to this new video. In this video, I am going to show you how to solve certain numerical problems which are associated with the de Broglie's hypothesis. Okay, so here I have noted down the first numerical problem for you. If you look carefully in this question, you will see that in this problem we need to calculate the de Broglie's wavelength. Of what? Of an electron. They have provided the mass of that electron, and that electron is moving with 1% speed of light. They also provided us the value of this Planck's constant. Now the question is how we can solve this equation. Now before I am going to solve this equation, let me write the mother equation which should be used to solve this type of a problem. That mother equation is lambda is equal to h, that is our Planck's constant, divided by mass of an electron. So I am writing it in the subscript, and the velocity. Okay, this is the mother equation. I believe all of you are aware about this. This is called the de Broglie's equation. Okay, now in this case, if you look carefully at this numerical problem, you will see they are asking us to find out the value of this wavelength. What they have provided? They have provided the value for this Planck's constant. They have provided the value of this mass of an electron, but they didn't provide the value of this velocity directly. Rather than, they have said the velocity of this electron is 1% speed of light. So how we get that value for V? Very simple. For that, we know the velocity of light normally we are representing with C, that is our 3 into 10 to the power 8 meter per second, right? I hope all of you are aware about these values because we are solving it for several videos. So I hope now you people can memorize this value or you can remember it. Okay, now we know the value of the light, and I need to calculate 1% of this, which is the velocity of this electron, as they have mentioned in the numerical problem. So what can we do? Therefore, the velocity, which is V of the electron, can be calculated as 1 into 3 into 10 to the power 8 divided by 100. What will be the unit? The unit will be meter second inverse. As simple as that. Okay, because we are not dividing it with any unit, so it will remain the same. So if I am doing it, it will become 3 into 10 to the power, it is 8 and this is 100, so it will be 6 meter second inverse. Okay, so this is how to calculate the value of that electron using the speed of light. This is the speed of light. We have taken 1% of it, and then this is the value. So once I have the value of this velocity, then the remaining thing is very simple. So we can do it like this. We need to provide the value for Planck's constant, 6.626 into 10 to the power minus 34. Okay, whole divided by the mass of electron, that is 9.1 into 10 to the power minus 31. Okay, multiplied by the value of the velocity that we got from this calculation. So this is 3 into 10 to the power 6. Now we need to simplify this one little bit to avoid any type of an mistake. Into 10 to the power minus 34. One thing in this context I want to say, if you can do it very fast, go ahead. I have no problem with that. But if you are not that much used to, I will suggest you to do it step by step. Okay. So this one 9.1 into 3 into 10 to the power, here it will be 25. Yes, minus 25. Okay. So again I am doing it once again, writing it in this way, 9.1 into 3 into 10 to the power, this one will be plus, so it will be minus 9. What will be the unit? The unit will be meter. Let's see how the unit meter is coming. Okay, so this is very simple. For that, what we need to do, we need to put the unit for all these values. One, the Planck's constant. Planck's constant, that value is, the unit kilogram meter square second inverse, that they have provided. Now the mass of electron is given in kg, and the velocity of this electron, that is coming in meter second inverse. Okay, so this is the units. So I am cancelling out this one and this one. If I am cancelling it out, then it will remain meter. So you can see that how we are getting the unit in meter. So that is what I have mentioned here. Now the rest is very simple. We need to multiply this one and we will get that value. Okay, so for that we need to use a calculator. Without that also you can get this value, but you need to go for an approximation, and certain times if you are making approximation which is, say for example, differed by 3 or 0.003, you will find a huge difference in the final result. So to avoid those kind of a thing, in the video I am using a calculator so that we get the exact value. So if I do this calculation, 6.626 divided by 3, which again need to be divided by 9.1. Where is 1? Yes. So what we are going to get? We are going to get 0.2427. I am not taking more than the 4 digits after decimal. 10 to the power minus 9 meter. You can leave your answer here, or if you want to make it a little bit better, you can write it 24.27 into 10 to the power minus 11 meter. So this is our answer. Here you have seen how we got the final answer. So this numerical problem basically little bit simple. Only small thing is that you need to calculate the velocity using this relation, that is 1% velocity of light. Not only that, if by some mean you forget the value of the speed of light, then you are gone, you cannot solve it. So that's why I am always suggesting the students try to remember certain values, because some numerical problem they will provide this value. In some numerical problem, as you can see here, they have not provided the value. So if a student is not aware about this value, he or she will not get that answer. Okay, so this is, I hope all of you have understand how to solve this type of a problem. Here we use this mother equation and calculated the value of this velocity of that electron in this way. Okay, now once it is done, we'll move to our next numerical problem. Let's see what are the other type of problems they can ask. Sorry. Okay, so the next problem. The next problem is little bit difficult, but calculation wise it is very simple. So what they have mentioned in this second problem, they are saying two particles are there. A and B. Okay, both are in motion. Now, if the wavelength associated with the particle A particle A is 5 into 10 to the power minus 8 meter. Calculate the wavelength of the particle B. If its momentum is half of A. If its momentum is half of A. Okay, so this is our problem. Now let's see how we can solve it. As you know that we are solving the numericals based on the de Broglie hypothesis, so you know what is the idea of that. So if I read that this numerical problem, we have two particles A and B, both are in motion. Now they have given the wavelength of only one particle, that is particle A, and the value is 5 into 10 to the power minus 8 meter. Now what we have to do, we need to calculate the wavelength of particle B, and they have given one condition, the momentum of B is half of A. Now what is momentum? You know that when you went for the de Broglie's hypothesis, you know this, the product of mass and velocity, that is nothing but the momentum, right? So what I will do, I will write the equation for both particle A and particle B separately, because here I have understand that it is basically the relative value. Relative value in that sense, if I know the relation between A and B and if I take the ratio, easily I will get the answer of this question. So to start with this numerical problem, I am just considering the wavelength associated with particle as lambda A. That will be is equal to h is a constant, divided by mass of A, and let's say velocity is equal to A. So this is for particle A. Okay. Similarly, I can write lambda B, that is the wavelength associated with particle B as it is in motion, is equal to h by mass of B and velocity of B. Now what they have said in our question? In our question they have given the momentum of B is half of A. So what will be the relation between momentum of A and momentum of B? As per our equation, as per our given numerical problem, they are saying MB into VB, that is the momentum of particle B, which is half of the momentum of particle A. So this is the momentum of the particle A. Okay, so like in this way we'll get the value for MB into VB, that means the value of this. So now if we are taking a ratio, we can write, so let me put this one as equation 1 and this one as equation 2. Okay, so dividing 1 with 2, we can write as lambda A by lambda B. Okay, this is equal to h by MA into VA multiplied by MB VB divided by H. Okay, now we know the value of this. which is half of MAMV. So what I'll do, I'll substitute that one. Lambda A by lambda B will be, let me simplify this one. So it will be half of MA MB, sorry, MAV divided by MA into VA. So how we are getting this one? Here I am writing using the value of MB VB from equation 3. Okay, I am writing this one additionally so that all of you can understand. So the last stage of this numerical problem is, we are almost there to get that answer. I am erasing this part and I will take it in this side. So they have provided the wavelength for A, that is 5 into 10 to the power minus 8. So I'll put this value 5 into 10 to the power minus 8. I am not writing the meter right now. I'll show you at the end. Okay, so what I have done, I just put the value for lambda A. Now this one will be is equal to, this one will be crossed out. So here it will be half. So lambda B will be 5 into 10 to the power minus 8 into 2 is equal to 10 into 10 to the power minus 8. Unit will be meter. Okay, or if you want, you can write it 10 to the power minus 7 meter. So this is the answer of the given problem. So here you can see that this problem is based on that idea. Here we no need to use the value for any constant, as we have seen in the previous numerical problem. Here, as I understand that they are giving the relation between the momentum of A and B, so I am taking the advantage of that. So I get that value MB and VB in terms of MA and VA. After that, simply I provided it here and I got that answer. So this is how to solve this type of a numerical problem. Now once it is done, then I will move to the third numerical problem. Okay. Okay. So our third problem is calculate the mass of a photon of sodium light. Having wavelength (5894 angstrom). 5894 angstrom. Okay. And velocity (3 into 10 to the power 8 meter second inverse). Okay, they have provided the value for each. The each is equal to, here they have given only 6.6. okay, so we'll use this value, into 10 to the power minus 34 kilogram meter square second inverse. Okay, so they have given the value of h and we need to calculate the mass of the photon. Now before we are going to start to solve this problem, here if you see, only little bit surprising thing is that they didn't say electron directly, rather than they said the photon of sodium light. Now the question is how to rationalize this one and how we can correlate it with the mass of an object. So to understand that, we need to remember that we have used that the radiation in the form of a particle. So here actually they are talking about a particle in the name of the photon that is coming from the sodium. So that's why photon of the sodium light. So you should not be confused with this phrase photon of sodium light. You just take it as a as the particle nature of light. Then everything is very straightforward. So to show you this thing only, I brought this numerical problem in front of you. So now that once you understand this concept, it is very simple. They have given the velocity, they have given the wavelength, and they also provided the value for h. So what we need to calculate? We need to calculate the mass. Okay, so again we'll use that mother equation, lambda is equal to h by mass of that particle into the velocity. So here they have given the wavelength, but the wavelength is given in angstrom unit, where you will see that the Planck's constant that is given in the SI unit. Therefore, first thing is to convert this angstrom to meter. So what I can write? I can write 5894 into 10 to the power minus 10. Okay, this is the only thing you need to take care of. If you can do so, I hope all of you will get the correct answer. So now let me put this value. Here I am using 6.6 as they are given in this problem. What is the mass? Mass I don't know, so let it be like this. What is the velocity? Velocity they have given in SI unit. Mass into 3 into 10 to the power 10 to the power 8 meter per second. Let me write this one this time so that I can show you, or you can see how the units will be simplified. So let me show you first this one, cancellation of the unit. Okay, mass is gone. This mass I don't know, so what is left over? Only the kg. So it is expected the mass what we are going to get, that will come in the kg unit. Okay, so now mass can be written like this: 6.6 into 10 to the power minus 34 whole divided by this value 3 into 10 to the power 8 into this one will come to the denominator. So 5894 into 10 to the power minus 10. So what is left over? Only the kg unit. Okay, so we need to simplify as we have done previously. 6.6 divided by 3, you can divide it if you want, it will be a little bit easier, into 10 to the power minus 34. Here it will be into 10 to the power how much? Minus 2. So altogether I can write 2.2 divided by 5894 into 10 to the power minus 34. Okay, that means 32. Okay, so now if I divide it, let's see how much the value is coming. So here 2.2 divided by 5894, that is 0.03732. 0.0003732 into 10 to the power minus 32 kg. but it doesn't look good. There are 3 zeros are there. So what I am going to do, I am going to take it as 3.732. Then it will be 10 to the power minus 36 kg. So this is the answer. I believe that out of the 3 questions, this is the most straightforward question. Very simple. Only this one. If you understand this one, if you are taking the light as a particle, then everything is very straightforward. Okay, so this is how we can solve this problem. Now I will move to the next problem, and perhaps that is going to be the last problem from this de Broglie's hypothesis. So let me erase it and write down the 4th question. The 4th question is about kinetic energy. Let's see. An electron moving with a kinetic energy and of 2.275 into 10 to the power minus 25 joule. Okay. They have asked to calculate its de Broglie's wavelength. Okay, very straightforward question, and they have provided mass of an electron. Mass of electron, already we know that one, but again, as they have mentioned in this question, I am writing it once again. 9.1 into 10 to the power minus 31 kg, and H, Planck's constant, they have given 6.6 into 10 to the power minus 34 yes, Joule second. Okay, these are the information they have given. So how to solve this question? This question is little bit different than the previous 3 questions, right? That is very clearly evident here. Here they have mentioned the kinetic energy. They didn't provide the velocity, they didn't provide the wavelength. They are asking us to find out the wavelength. What they have provided? The kinetic energy, and along with this problem, the mass of an electron and the Planck's constant. So what we know so far, whatever we have used to solve the previous questions, that is our mother equation, which is m, as it is electron, so I am writing in the suffix velocity. Now if you look at this equation and try to fetch the information from the given problem, you will see this one we need to determine. H they have provided, mass they have provided, but the velocity they have not provided directly. Rather than they mention the kinetic energy is equal to 2.275 into 10 to the power minus 25 joule. Now in this case, to get the velocity, what we need to, from where we will get this velocity? We will get this velocity from the kinetic energy, right? This is the only source left. So we can understand that somehow we need to get the value of this velocity from the kinetic energy. Now, as you have already learned, kinetic energy, in short we are writing Ke, which is equal to half mv square. So here it is the mass of an electron and the velocity v square. Now they have provided this velocity, this kinetic energy. So what can we do? We can write according to the problem, according to the given problem, half mv square, which is the kinetic energy, is equal to 2.275 into 10 to the power minus 25 joule. Right? This is what they have given in the numerical. So now from here I can easily calculate the value of v square. So v square will be 2 into 2.275 multiplied by 10 to the power minus 25. I am not writing the unit anymore. I will show you at the end. Okay? Whole divided by your mass. What is the mass? Mass is 9.1 into 10 to the power minus 31. Okay? So let's see how much it is coming. So I am multiplying this one because this is very easy. 2 to 4. Let me check it. No, 0, 15, 5, 1, 4, 5. Okay. 9.1 into 10 to the power. Now this one will be how much? 6 plus 6. Okay. So if I solve it little bit, or we can go for rough approximation by considering it as 4, but that will not be good enough because value will be deviated a lot. So let's see what is the value for this 4.55 divided by 9.1. Let me calculate it at this stage. So 4.55 divided by 9.1. This is coming 0.5. Wow, that looks pretty good. So this is 0.5 into 10 to the power 6. Now the unit will be meter square second inverse square. Okay, let's see how this one is coming. I cannot write anything arbitrarily. There should be a definite reason behind it. Now let's put the unit over here. We know one thing, that joule, 1 joule can be represented as kilogram meter square and second inverse square. So if I use this unit for for joule, then this is what they have mentioned here, right? So let me put this value, kilogram meter square second inverse. So that value we are dividing it by what? By mass. That means kilogram. Okay, that is the mass of an electron as they have mentioned here. So kilogram will be nullified and it will remain as m square second inverse square. That is what I am writing here. So once I got this value, easily I can get it. Achha, let me write it this side. So therefore velocity will be root over of 0.5 into 10 to the power 6 meter square second inverse square. Okay, so if I am doing it, I need to use the calculator once again. I believe that it will be around 0.07, but in any way let me check it correctly. So this is 0.5, it is 7071. Okay, so if I am taking the root over 0.7071, then it will be 10 to the power 3. Okay, unit will be meter second inverse. So velocity unit has come in meter second inverse, which looks pretty good. So this is how we are going to get the value of the velocity. Once I have got this one, now you see, you provide the value of the v and you will get that answer. Okay, so let me show you how to get the final answer of this problem. We are using this equation once again. We calculated the velocity from the kinetic energy. Now I will substitute that value in this equation. So this one will be is equal to how much value they have given, 6.6. So they make our job little bit easier. 10 to the power minus 34 divided by the mass, that is 9.1, into 10 to the power minus 31. Okay, into the velocity, this is the velocity, 0.7071 into 10 to the power 3. Okay, so we can write 6.6 divided by 9.1 into 0.7071. Let me put the 10 to the power minus 34, here it will be into 10 to the power, 10 to the power 34, here it will be 28 minus 28. Okay. So 6.6 divided by 9.1 into 0.7071 into 10 to the power 6 minus 6, right? Yes. What will be the unit? Unit will be in meter. As we have done in the previous numerical problem, if you are putting those units, you will see that it will be ended up with the meter. That is the unit of length. Now we need to again use the calculator to get this value. This one will be 6.6 as they have mentioned. 6.6, where is the 6? Divided by 9.1 whole divided by 0.7071, and the value is coming 1.0257. 1.0257 into 10 to the power minus 6. If you want to express it in nanometer, then it will be 1025.7 into 10 to the power minus 9 meter. That means 1025.7 nanometer. Okay, so this is our final answer. So this is the wavelength associated with the electron which is moving with certain kinetic energy as they have given in the numerical problem. So here you can see how easily we can solve the numerical problem associated with the de Broglie's equation. In this case, very simple. You need to figure it out how to get the value of this velocity. Sometimes they can give this value in terms of kinetic energy. Sometimes they can compare it, give a comparative value with some other constants, like we have seen in the first numerical problem, 1% of the speed of light. Okay, so in any way you can easily find out the value of this velocity. Once you have this one, then simply you provide those values and you will get the correct answer. If you are not making any mistake in the calculation, for sure you will get the correct answer. Okay, so that's all for this video. If you like this video, please subscribe it, and in the next video we will bring some numerical problem associated with the Heisenberg's uncertainty principle. Okay, thank you for attending this video.